Fantastic. Okay. So yeah, good morning, afternoon, evening to everyone online. So what I'm going to be talking about today is the Solar Orbiter Python working group, some updates and some plan forward and what we're doing. So I'm going to give this presentation, but really it's Giovanna and Clementina have put massive effort into putting these slides together. And it's really updates from a larger working group that we've been kind of looking at the Python aspects of working with Solar Orbiter data. So this is really a talk on kind of the updates and plans and what we have been doing and what we plan to do in the future. And one thing we would like at the end of this is to get some feedback from people, right? Because it's working with the Solar Orbiter data and to help guide this working group for, collecting our resources together to get the most science we can out of the Solar Orbiter observations. So just to begin, why do we need a Python working group and why do we need to think about some kind of software ecosystem with working with solar data, right? We are in this unique golden age of heliophysics, but with that comes a really diverse data landscape, right? So with Solar Orbiter, for example, we have two very different types of observations. Remote sensing, so taking images of the sun in different wavelengths. We have then in situ measurements of measuring, solar wind at the spacecraft or magnetic field. And these two things are quite different already, just in how their data and observations are in terms of analyzing them. Then with Solar Orbiter, of course, and with Parker Solar Probe, we're now living in this era of multi-messenger observatories. So we're looking at the sun and probing the heliosphere with very different viewing points that we're used to maybe with having spacecrafts orbiting the Earth. So that brings in another dimension of making the data more diverse and kind of maybe more challenging to use in some circumstances. We also have lots of ground-based observatories, which of course come with their own challenges, but combining these with remote sensing or combining these with multi-messenger observatories, we need to think about. And then, of course, with Solar Orbiter, we do lots of these super coordinated campaigns when Solar Orbiter is at perihelion during the remote sensing windows, where we're kind of doing targeted campaigns of different parts in the sun with different scientific questions, different modes, different viewing angles, which makes it challenging. So in an ideal world, as a scientist, you want to be able to import some Python package. You want to be able to get all the data, analyze all your data, and maybe write your paper. It's a bit of a joke there. But this is really the motivation behind this working group, right? So we want everything working within an ecosystem so that from a user point of view, it's very easy to actually do the science we want to do rather than this bottleneck of trying to figuring out what data exists, where to go, how to get it. And really, as a scientist, your thing should be you want to get your data and prove your hypothesis, right? And this is the whole idea behind the MADAWG Python working group working within the SunPy ecosystem to kind of make this a little bit easier. So I guess with Solar Orbiter, we have this opportunity, which I've touched on, right? It's designed to be this multi-instrument and multi-viewpoint science spacecraft. A lot of us, work maybe on one instrument, and we use one instrument to do science to look at the sun. So, for example, I work with STIX observations a lot, and some of the time I only use STIX observations, which is fine, and that, of course, answers some scientific questions. But to really gain the most out of Solar Orbiter and the opportunity it provides is to be able to do multi-instrument science together, right? So using different remote sensing and in situ measurements on board in kind of one scientific capability. So this is, I guess, the opportunity it provides. We have these multi-instrument observations, so the 10 different instruments on board. We have this for the same CME, for example, or flare, we can observe it across a whole multitude of observations of remote sensing and in situ. We have this unique vantage point, so away from the sun-earth line, and we can do these coordinated campaigns where we have kind of high cadence resolution and designed for really doing this joint analysis. So as we know, we're on this call, Solar Orbiter really opens up some exciting new ways for doing solar and heliophysics science. However, with that, as I've mentioned, there are lots of challenges, right? And one of the ones that we've kind of come across, and one of the aims behind this working group, is to do this multi-mission science is difficult, right? For Solar Orbiter, it can be sometimes very hard even just to find when data is available and when data is available in a specific observing mode that you're interested in, depending on the instrument that you're using or the campaign that was run. This plot here to the right, this is actually on the Solar Orbiter archive website that you can see. This is created by Eric Bouchelon. And this shows, it's kind of difficult to see here, but these are all the different data products from different instruments on board Solar Orbiter, and then the availability of that data on the Solar Orbiter archive. So sometimes if you're not totally familiar with working with Solar Orbiter data or knowing exactly what it was doing when, if you weren't involved in a campaign or anything like this, it can be sometimes a challenge to find out when that data is available. And again, if you've ever tried to work with solar orbiter data, even with one instrument, it can have many, many different modes that it operates in. And that's the uniqueness of solar orbiter, that it can run in a different mode for a specific science case. But then if you're going back to the data after the fact, sometimes it can be challenging to figure out what mode you need and what mode was available during the time of interest. There are also, the challenge as well with Solar Orbiter in some sense is that, compared to some missions like SDO, there's just continuous data all of the time. So you never have to really go check if it's available, it's there. So sometimes there are data coverage gaps, different coordinate systems, and then time matching between instruments. So say you want to understand that this event was observed by these two instruments, is there a latency between an event seen from one instrument and another instrument? So that's kind of some of the challenges with even just finding and combining the data. Then once you find your data, it can be challenging to work with the data, right? So we have lots of different tools for different instruments, which is great if you're doing your own instrument science. But if you want to do this coordinated multi-instrument science, it can be a bit challenging. To date, we really don't have a consistent workflow. And what I mean by that is, you can easily import a package, load in all your data from all the different instruments, do all your science, and go away with it. That's still quite a challenge. And a lot of the times the knowledge is there, but it's not necessarily documented anywhere, right? So it's siloed within an instrument team or within a group. And not that it's been hidden, it's just that it hasn't really been documented well enough for a wider general community to look at. And again, if we're thinking about the challenge, like some people will then go and write their own code, right? So to do one specific thing, and everyone's kind of reproducing their own, doing the same thing over and over again. Whereas a community effort, we can really think about how can we solve this in a larger way. And the current barriers to some of these challenges are, again, the scattered tools. So someone makes a tool and it lives in one place, or maybe it's not online, then somebody creates a different tool, and that can be a challenge. Of course, documentation gaps. So trying to find documentation on specific instruments or specific science cases for when the data is available. Duplicated efforts, as I mentioned, and then there's postdoc risk. So having sustainable software. So maybe there's a postdoc that is hired to work on some software to make some analysis tools, and then they leave to a different contract and that software isn't maintained. So how do we as a community overcome these barriers to kind of overcome this challenge to actually do the science opportunities that we really want to look at? So this is really the aim of our working group, right? Is to look at all these challenges. We now have all this amazing data with Solar Orbiter, and how can we overcome those challenges to take the opportunity? And this working group falls within the modeling and data analysis working group called MADAWG, which is one of my favorite acronyms. And we kind of came together to look at specifically looking at Python tools for doing this multi-instrument science. So the aims of our group is to basically centralize a place for all the available Solar Orbiter tools and efforts. So we kind of know what each of us are doing, and we can kind of centralize that in one place so somebody can find us. We also want to scope the needs and identify gaps, right? So we know there are some things that are working really well, some things that are not really working well. There's gaps in being able to do this. So how can we bring instrument teams together and coordinate across these for identifying the missing data gaps, and then to be able to develop them into the future? We also want to develop and document common tools. So for example, um, so maybe having a standardized catalog across all of Solar Orbiter, whether a flare was observed with different instruments, or can we have some consistent way, and that it's built once and then used by everyone. So again, we're not doing the same efforts over and over again, and this makes the kind of science workflow more seamless. And then facilitate data access, right? So we have an amazing Solar Orbiter archive, and SunPy integrates it in with that quite well. But how do we then go that extra step further to help a user find the data that they're interested in? So these are kind of the four main things, but overall, the aims of the working group is to really enable the science and kind of have these user-ready analysis workflows in Python that will enable the science that we want to be able to do. And so before we did this, right, I gave actually a talk at one of the first sessions of this webinar series. A lot of things already exist, right? So what does exist and what is missing? So how does SunPy fit within this Python working group? So SunPy is a large project, which many of you have probably worked with before, for having a collection of SunPy core package and a whole ecosystem of affiliated packages for working with Solar Orbiter data. So we know that lots of tools exist, and a lot of tools already exist in SunPy to work with Solar Orbiter data. And a lot of it exists before we even realize that it's there, right? So sometimes people go and develop their own thing and didn't realize it maybe was already developed within SunPy, and it just wasn't realized that it could be translated to work with Solar Orbiter data. And what exists already, right? So data access to get Solar Orbiter data is available through SunPy, through our affiliated package SunPy Soar. One of the powers of SymPy is doing coordinate transformations, which has become increasingly more important, obviously working with solar orbiter data. We have data containers for working with maps and time series. We have ways to look up multi-mission observations and combine them together, and plotting and quick look tools. Right, so at a high level, there are lots of things that already exist there, but there seems to be kind of in some cases, a missing gap with being able to, I guess, fully utilize the power of SymPy with using solar orbiter data. And a lot of the time, it's really just discoverability and tailoring the cases to have workflows that work with the solar orbiter data. And this is, again, what we're trying to do. We're not trying to reinvent the wheel with this Python working group. We're trying to build on what already exists within this whole SymPy ecosystem and then kind of tailor the needs of what's needed by the solar orbiter community. So what have we done so far as a working group? So we formed in late 2024 under MADAWG. So we kind of started having kind of monthly meetings. So the working group consists of many different people across different instrument teams are involved in Solar Orbiter. So kind of getting the perspective from different aspects of working with the data, whether it be from data pipelines to actually user tools. We started with a community survey from instrument teams specifically. So from specific instrument teams, what tools did they use? What did they have? What do they know is a challenge to do? What is the current gaps? We kind of cataloged current loading and what tools exist and to what level are they integrated within the SymPy ecosystem. We've identified some priorities now that we're kind of build on, documentation being a key one, but then looking at a higher level, what common data containers can we create before we even build the most specific tools for working with Solar Orbiter. And we now have kind of a centralized doc hubs that we're hoping will grow to be this place for the one-stop shop for working with Solar Orbiter data in Python. And we'll talk a bit about that in a moment. So where are we today in terms of working with Solar Orbiter data within the SymPy ecosystem or within Python? So these are our initial survey results. Again, these are the survey results just within the instrument teams. In terms of general support, we're pretty good support in terms of accessing the Solar Orbiter archive or SOAR using SymPy SOAR. There are also other kind of API protocols to access the SOAR as well if you want more specific searches, which is working quite well. In terms of data containers, which are useful, we have maps. So again, remote sensing images of the sun, but only 2D is something we only have to date. We have time series. So again, looking at anything, one-dimensional time series. So measurements as a function of time. And we have NDCube, which is a SymPy affiliated container for working with basically any more than 2D maps, so 3D maps or any kind of dimensional maps that you might have. And this is useful, for example, for spikes. And then for coordinates, we lean heavily on AstroPy and SPICE. So kind of generic support exists for working with Solar Orbiter data, but instrument-specific things itself, these are kind of just looking at the remote sensing and in situ. And so we have basic support for most instruments on board Solar Orbiter within Python. The green ticks is like fully supported within SymPy, works very well, very low barrier to entry. The little kind of lightning bolt means kind of active development, right? So there are tools available, they work well, but maybe are going to be developed further and maybe can do with kind of some more help in terms of the user community to help them build them a little bit more. So I think the takeaway here is we are getting there, right? We have seen that there's lots of efforts going on and you can do a lot of the scientific needs that you might want to do within Solar Orbiter, within SymPy, excuse me. So this is kind of where we are today. And the key issues we've identified, so we kind of know we're doing okay, but what are these key issues? And I've already kind of talked about these challenges, but we've really identified these. So scattered tools. So if you want to, maybe you didn't know a tool exists, but some group has a tool that they work really well and is open source and available, but the discovery of that tool can be challenging to find. So we want to make sure that this is accessible to the wider community. There are some documentation gaps. So, trying to find specific documentation for working with the data can be challenging and then makes it harder to access data for new users. We have some good containers, and when I mean that, again, data containers to hold your data, pretty good for map and time series data, but a bit more challenging for two-dimensional or three-dimensional data that aren't maps. So things about electron velocity distribution functions and things like this, we don't really have a good container for that, or things like radio dynamic spectra. We're kind of working on that, but again, there are some missing containers for interlinking and working with those two things together. There has been a lot of duplicated efforts, which is fine, but again, it would be great if we can join our efforts together to not duplicate things and to kind of waste time or energy in terms of doing the same thing over and over again. We don't have a standardized catalog, and I think this is something that I personally think is quite important, and hopefully we'll work more so on our working group to have a standardized solar orbiter catalog, whether it be for CMEs, whether it be for ICMEs or flares or SEP events. There are, of course, many catalogs that have been created, which is amazing, but it'd be really nice to have a standardized way that could be easily integrated between several of them. And again, visualization tools can sometimes be a key bottleneck for science. So this can be even just for quick look data for trying to identify events that you're interested in. But again, we have identified these challenges, but we've also kind of had some test cases for maybe trying to work with solar orbiter data on a larger scale Python way. And I just want to highlight this was if anybody's interested in this, this is the QR to this GitHub page. So in January in India, we had a ISRO ESA workshop, and as part of this, a large portion of this workshop was actually a hands-on session to learn to work with solar orbiter data and ADIS with data, L1 data, and Proba 3. But it was a good test case, and this working group was heavily involved in putting together notebooks and tutorials for working with the solar orbiter data individually with each individual instrument, but then also doing a science workflow. So again, if you want to look at this, we have some in the solar orbiter repository there. There is tutorials for each of the different instruments on board solar orbiter, which are kind of updated from ones we did in 2022. And this was quite powerful, I guess, from the working group perspective that we were able to contribute to this, but also highlighted a lot of challenges and some other kind of key insights that we need to focus on, specifically about dependencies of different Python packages. But one thing I want to say is we also tried to do these science workflows. And this was a real test case. This was really nice work done by the MEDIS team, by both Giovanna and Clementina online, where, it's great to have code to work with one specific data or to read it in, but what about doing a science case with that workflow, and how did that look? So the idea here was to try and use Solar Orbiter and Proba 3 and supporting observations for a multi-view CME observation. So analysis of 3 distinct vantage points of looking at, say, a CME. And in this workflow, again, this is also on the GitHub, and I'll show that in a minute. The workflow is really, okay, as a scientist, how can I go from my data access, querying the data, trying to find the data, then visualizing that data, taking into account the different coordinate systems, then applying a 3D reconstruction using the GCS model, and then actually doing scientific analysis for getting the CME kinematics. And why this was a really excellent test case, I guess, for stress testing the Python working group and the gaps is a live testing of the Python tools, right? So it's great to say we have Python tools, but how do they actually work well when trying to do your scientific analysis? Specifically for a hands-on workshop with lots of people. So it demonstrated, we're pretty good at getting the data access. We can really do this modeling, but exposed gaps. And even doing this was still a challenge, but they did a lot of work into getting this with workflow, and how can we do this more consistently? So I guess the conclusion is this case really shows how fragmented some of this workflow can be. But by doing it this way, it actually helps guide what we really need to do as part of this working group. And this is just an example. Again, this is available on that GitHub that was at a QR code, which showed how you can actually really do this all within the Python and SciPy ecosystem, which is really nice. So highlights the power of doing multi-instrument science. And hopefully it's going to help us with the opportunity to make it a little bit easier and more accessible to people who maybe are not as familiar with working with the specific data products or what needs to be done to actually perform this type of analysis. So again, if anybody's interested, please go and look at the GitHub repository. And these slides will be available online afterwards, or maybe someone can put it in the chat, a link to the GitHub. Some other updates is that as part of this working group, we've identified, we have lots of tools within SciPy, but maybe not specific to Solar Orbiter. So the FEE team and the MEDIS team have done an awful lot of work to actually make source-specific maps that are now being integrated within the SciPy core. So there are 2 open pull requests to SciPy core currently under review to make they follow the standards that SciPy kind of enforces. But this is quite exciting and a really good update to see kind of the integration that Solar Orbiter data has within the wider SciPy ecosystem. I think this is really important to have shared data containers so you can easily download your metadata, easily load it into a map, and it will understand, where the coronagraph is and all of these things. So I guess just an update takeaway is that we're really kind of working now to try to really integrate this further and working with the SciPy developers some more to help with that. And the idea in the end of the day is to have one ecosystem enabling multi-instrument science. So this is kind of how we're integrating with SciPy. And I just also want to mention that it's not that everything needs to go into SciPy at all. So these these are kind of core map sources, so these can live within the SunPy core package. But SunPy affiliated packages are an excellent place for packages to live. So for example, StixPy, which is a Python package for working with Stix data, that is an affiliated package of SunPy. It's maintained by somebody else that's not necessarily, well, they are linked to SunPy, but they don't necessarily have to be, and completely maintained by the instrument teams. And similarly with SunRaster and SOSpice for working with Spice data. It's again, developing these within the SunPy ecosystem. What we've also kind of developed, and this is something we would love help with by the community, is we've developed this Read the Talks webpage. So a documentation resource as a place for lots of data to live, or not data, excuse me, links or tools or examples to live. So it's openly developed on GitHub, so anybody can contribute. Right now, you can make a pull request, or you can send us an email if you don't know how to make a pull request about adding some user guides or tools for this. The content so far is quite bare, so our plan for as a working group is to populate this. So we have some getting started guides, we have links to some specific packages, and we have an example gallery. So there's kind of already some examples there of kind of maybe accessing the data or plotting the data for different instruments. And we're hoping over the next year, this will become really a place where anybody can go and see how to work with the different data products, or you'll find a link to the instrument specific web pages. Another good test case for showcasing, I guess, where we are with using Python tools for working with solar orbiter data. This was a really nice hackathon that was organized by Miho and others at ESTEC, which happened in November of last year. And the Python working group, our MADAWG Python working group, wasn't necessarily involved in a lot of this, but it was really good insight to kind of, again, identify where the positives are in working with solar orbiter data in Python and where some of the challenges are. So these are just some snapshots of things that, you know, the different teams were able to do within Python. And we're hoping to kind of use all the tools and analysis that they developed to help kind of guide again our Python working group. And we're hoping this was all done through ESA Data Labs. So hoping maybe we can use ESA Data Labs in the future to showcase working with solar orbiter data, different workflows and things like that. So I'd say watch this space. I think there's going to be some webinars coming up of the results of this hackathon in the next few weeks. One call for help from you all is that we did a survey, and I've talked about identifying lots of the gaps for working with solar orbiter data in Python to help guide what our working group is going to do. But we realized in doing that, we all work with solar orbiter data as well. We're already quite involved in solar orbiter, and we really need user feedback. And you know, what are your needs and what is not clear with working with solar orbiter data? So we currently have a survey open online. There's a QR link here, or you can find it. I think it was on Solar News. And the idea here is, again, to guide our priorities as a working group, right? So we're kind of at a stage now where we kind of know what we need to do, but where do our priorities need to lie? And this will kind of help us iterate and hopefully find some people who are interested in also in guiding us there. So it's been up for a week. We have some really good insights already. And what we're hearing so far is one of the biggest challenges, again, is just finding the right data products, levels, and availability, right? We're in a position now where we have over 5 years of data from Solar Orbiter, but still it can be quite a challenge to really identify the data products that you're interested in. And there's a strong need for clear documentation and examples. So again, this is something that we were aware of, but it's actually very interesting hearing it from everyone else too. And maybe this is now going to help us that really it's the documentation and worked examples are the thing we really need to focus on looking into the future. So please, I would highly recommend anybody to take this survey if you want your say, or please share it with your colleagues and help us kind of guide our efforts over the next few months. So what is our plan ahead, right? So we've done some things, but we have big ambitions to do more. We currently, you know, understand the needs. We are now in a position where it's working with the different instrument teams and within our working group, we kind of understand the needs now. We understand really, you know, what we kind of need to focus on, where the gaps lie, and how can we really align this with the existing tools. So what does exist in SunPy and what can we extend to make it more discoverable with working with solar orbiter data? So I think we're kind of pretty good with that now. We're now trying to building the foundations for kind of the roadmap ahead. So we have this place where we can put all our documentation. We just need to now populate it. So we need also help from users and from instrument specific teams to help populate that with user guides and working with the data. We have, looked at shared data access and discoverability, and there's lots of work going on with the Solar Orbiter team to help with that. And we've kind of identified these common tools and containers. And I think we've highlighted the largest container that we really need to work on from a larger scale project for working with different types of data products. And we're hoping that what this is going to be able to do is enable science. So maybe a hackathon next year will do full workflows all within the SunPy ecosystem that will work quite well from this end-to-end analysis. So this is our roadmap ahead. I think the data is ready and the science is there. It's just really making sure we kind of lower that barrier of entry for the tools to unlock. And, get involved. We need your help, right? So please submit the survey. If you have small examples of working with Solar Orbiter data, we would love to see them and put them onto the documentation website. If you have any tips for working with different instrument data, or if you'd like to contribute to the GitHub. I'm leaving some links here. So on the SunPy website, we already have some examples of working with Solar Orbiter data. On our Solar Orbiter docs, we're adding some here. We also have, again, this GitHub page where we had the hands-on session at the ISRO ESA heliophysics workshop is a really good starting point for working with the data because they were developed as to really showcase how to start with the data. And, I'm hoping in a year's time we can give another update and we will say we solved all of these problems. But I think we've made a huge progress in really identifying what we need to do as a working group. And with that, I will finish. But if Clementina or Giovanna have anything to say or want to jump in, please break away. Thanks, everyone.
Thank you, Laura. You have provided a very complete overview, so I have not any more to tell. But I think that what comes across strongly is that this is not just a software project; it's a community effort to make solar orbiter science more accessible, more reproducible for everyone. And the foundation is already there with SunPy, and as Laura has expressed very well. And from my perspective, the most urgent priorities are exactly what the survey is confirming. So documentation, shared workflows, and there are things that every team benefits from, and there are also contributions that anyone can make. So not just software developers, but also scientists, also senior scientists that come from the ideal world, because they have a great experience and a global perspective to contribute and provide feedback. So we encourage again everyone to engage, to fill the survey, to share the knowledge, and a small contribution is very important for us. So thank you very much.
Okay, brilliant. Thank you, everyone.
Yeah, from my side, nothing to say. So waiting for questions from the community.
Brilliant. Thank you.